Welcome to everyone. Good afternoon, and welcome to this new seminar. Today we will have Yael Hillman, and she's going to speak about cataclysmic variable, a unified theory of cataclysmic variable. Just a few information concerning Yael. She got his PhD position in 2016 at Tel Aviv University, defending a thesis on the long-term evolution of nova binaries. And after that, she had two postdoc position, one in New York and the other one, which is still in course at the Ariel University. And just as additional information, I want to recall that she's involved, and this is important at least for me, in the formation of high school and middle school students, in particular in arguments close to astrophysics. So, in my point of view, this is very important. And so, please, yeah.
Thank you, Luciano. Okay, so I mostly work on nova eruptions, which is a nova is one of their cataclysmic variable, and recently published a paper that was titled "The Unified Theory of CVs." Most of what I'm going to present here is from that paper, a little bit from other places, and I will start. So just a tiny bit of a background. CV is a binary system which includes a white dwarf and a low mass main sequence star, a red dwarf, which are semi-detached, which meaning that they are close enough together for mass to be transferred from the red dwarf to the white dwarf, and many different variability is observed because of this mass transfer. One of them would be the classical nova, which is the main event, is what I would like to call it, which is an eruption that occurs because of a thermonuclear runaway on the surface of the white dwarf due to the accretion. The time between eruptions could be very, very long, could be tens of thousands of years or longer. And the typical accretion rate would be anything lower than 10 to the -8 solar masses per year. This is very estimated because it's a very wide range, but that's in general. Now there's also recurrent nova, which is basically the same phenomenon, the same mechanism as a classical nova, only since it has a higher rate of accretion, time between eruptions is much shorter, so we can observe the same system in eruption a few decades apart. Now, there are also dwarf nova, which is not a thermonuclear runaway. It has to do with instabilities in the accretion disk, and there's a wide range of different photometric variability that may be seen, different magnitude changes, different lengths of times. And for this, there's also typical accretion rates that would cause this. In general, below 10 to -9 solar masses per year. And of course, this is also, there's a wide range, so it can be a lot lower also. But my point is that different accretion rates will cause different types of variability that we call CVs. There's also nova-like, which is just a high accretion rate, which with no evidence of any kind of eruption, but we're seeing the high luminosity. Now, detached system would not really be called a CV, but I'm just putting it here for comparison that if there is no mass transfer between them, so from the red dwarf to the white dwarf, or at least it's low enough to be effectively considered as there is no mass transfer, so then these the system would actually be detached. Right? And I know this is not really, can't really call it a CV, but it's like the lowest possible accretion rate would be 0. So what we're seeing is that there are these many different types of CVs which are caused for different reasons from different phenomena. But what's setting the tone there would be the rate that the mass is transferred. So this raises the question: is this mass transfer for a specific system constant throughout its lifetime? So we have to see what causes this, what determines what the mass transfer rate would be. So we know that the reason why there is mass transfer is from Roche geometry. If we have equipotential surfaces of a closed binary system, then, so this is what it would look like, and I'm sure this is not new to anyone. And there is the first Lagrangian point in the which is a point between the two stars in which any particle that we may put there will feel the same gravitational pull to each star. Now, if the stars are in, so this would be the Roche lobes, okay? Now, if the stars are in this sort of formation where their radius is much smaller than the Roche lobe radius, they are detached. But in CVs, the formation is more like this, where the red dwarf is filling its Roche lobe, and then there is Roche lobe overflow, so that's what causes the mass transfer. So these are called semi-detached, and we have mass transfer, and this is just, I don't like using too many equations in presentations, so I just put this up here because this is the whole equation, and if we look at it more closely and just pay attention to this exponent, so we see that the accretion rate, the rate that the mass is being transferred, is very strongly dependent on how much overflow there is, and how much bigger the red dwarf radius is compared to the Roche lobe radius, because as soon as it becomes slightly bigger, or if it's just slightly bigger, then it's not going to actually live like that. All the mass will spill over to the white dwarf. So this very slight difference, which could be to even a hundredth of a percent or a tenth of a percent, is what will cause this spillage. And it's very sensitive. So any very little difference there will make a big difference on this exponent, and that can affect what the rate will be. Now, so the question is, what determines the Roche lobe radius itself? And it's intuitive, and also from Eggleton, we know that it depends on the separation and on the masses. The Q is just the mass ratio, and A is the separation. So we know that the Roche lobe overflow is sensitive to the Roche lobe radius, which is actually how much there will be Roche lobe overflow, is sensitive to separation, and the accretion rate is sensitive to this radius. So this means that what determines the accretion rate is essentially the separation. So the question of what determines or if the accretion rate remains constant is translated to the question of, does the separation remain constant? And we know that it doesn't remain constant. It's intuitively, we can understand that it will change, but how much does it change? Does it change enough to actually affect the accretion rate on orders of magnitude, or just slight differences? So how will it affect it? So after a nova eruption, we can recalculate the separation just based on the connection between angular momentum and the binary masses. And if we take this equation and differentiate it, we get something like that. And this can be written much more simpler in this formation, where this shows the change in the separation as a function of how much mass was ejected during the nova eruption, how much mass was accreted during the nova eruption, the white dwarf mass, and the red dwarf mass. And if we look at this, in almost every nova eruption, definitely in the classical nova eruptions, the ejected mass will be higher than the accreted mass. And even if they are very close together, Q can't be crazy. It has to be of order, between half and one or less than one. So whatever we do here, this will remain bigger than one. So the change in the separation will always be positive. So every nova eruption should result in the separation increasing. So before and after a nova eruption, we should see a difference in the separation, an increase. Now, of course, it's not a huge increase that can actually be observed, but if we're modeling, which is what I do, I know I'm speaking to an observatory, but I use models, there should be a slight increase in separation. And as we said, an increase in separation would cause a decrease in the accretion rate. Now, we have an opposite effect during the accretion phase. Now, an accretion phase, the amount of time that it takes for a nova to accrete the mass, for the white dwarf to accrete mass, as I, in the very beginning, mentioned that the time between eruptions could be 100,000 years, 10,000 years. So most of that is the accretion phase. The nova is very, very short relative to the time that it takes it to accrete the mass. So we have this very, very long period of time that the white dwarf is slowly accreting mass. And during this time, there are physical processes that are working. We have magnetic braking from the red dwarf and gravitational radiation from the white dwarf. Now, both of these are very, very weak. Magnetic braking of a red dwarf is weak because it has very weak winds, and white dwarf is not a very massive, very strongly gravitating body, but they do exist even though they are weak. And if it has 100,000 years to work, it can have an effect. So it would carry away angular momentum, and that would mean that during the accretion phase, the separation would decrease. So that means that the accretion rate would increase. So generally, if we're looking at one cycle of accretion of a nova, so what I have here is a logarithmic time scale and logarithmic accretion rate. And so the eruption is not in this graph, it's just the accretion phase. So it will accrete, and then the eruption is like at the end of that, and that's the end of one cycle. So we're expecting the magnetic braking and gravitational radiation to cause this picture of a slow increase in accretion rate up until the eruption. And then we would expect the next cycle, or cycles after that, to push the stars apart. So we're starting now at a lower rate, or it does not necessarily would have to theoretically start lower, but these are results of modeling, and the modeling are showing that it starts lower. So we would have another cycle doing the same thing. There is one effect that is neglected here, the donor irradiation. There are other effects that I'm sure I neglected, but I am now adding the donor irradiation into here. Since they are close binaries, the red dwarf is irradiated by the nova eruption, and that will cause it to not be in thermal equilibrium for a short while after each eruption. It will expand. And if it's expanding, so it will have increased Roche lobe overflow. So that will increase the accretion rate. This lasts for a couple decades, a couple centuries after each eruption. And that will cause the curve to actually look like this. So it will start out high for a couple hundred years, decrease quickly. This is logarithmic, I'm repeating. So it will decrease for a couple hundred years, and then slowly increase back until it has enough mass to erupt. Now, if we look at the rates here of these two example cycles that I put here, we can see that this regime at the beginning of an accretion phase, right after eruption and right before eruption, at least for these example cycles here, the accretion rate is typical of what we would see in a nova-like. And in between, after the effect of the irradiation declined and before it, before the separation started to decrease a lot, it becomes typical of a dwarf nova. So this means that it is possible for, during these 100,000 years of accretion, trying to reach the nova eruption, the system may be observed as a nova-like or as a dwarf nova, depending on the accretion rate. And of course, not every cycle may go through all of them, but this is a possibility that the accretion rate may change enough for the systems to look differently at different times of its evolution. Now, as I said, these are sample cycles from a model. So the model that I got these results from is a combination of two codes. One code that simulates the evolution of the red dwarf, all the way from it being a pre-main sequence. It can go all the way to a white dwarf, but it's not relevant here. I took the main sequence stage. And I got from the evolution code all the data that is needed to feed into the other code, which is a nova code. So they actually communicate. The nova code is a hydrodynamic Lagrangian code, and it can do even 100,000 of consecutive cycles. So this allowed results of simulating a model. This is one of the models I took as an example. This is a model of a white dwarf that was initially 1 solar mass and a red dwarf that was initially 0.7 solar masses. And this is again a logarithmic timescale and a logarithmic accretion rate where each curve is presenting a different nova cycle. And if you look at the color code compared to here, so as we move down, we're moving forward in time. Now, of course, this isn't all the cycles because were more than 15,000 nova cycles in this model, but it's representative. So we can see the trend of what was happening here. So as we progress in time, the accretion rate becomes lower from cycle to cycle, and therefore the time becomes longer. And we can see that if we started with a red dwarf mass of 0.7, the simulation went until it eroded the red dwarf down to a substellar object, down to below 0.1. And I just marked this line as under more or less 10 to minus 15 solar masses per year. It would be a detached system. It would be undetectable. So not every cycle would reach that, but at a certain point of evolution, it starts going into these deep, very long phases of, say, the cycles of 100,000 years, that it would be undetectable. And that is what is called in this community hibernation, which is a theory from decades ago that was just a theory. This model shows that it might be possible. Now, throughout this whole evolution, what's happening is the white dwarf is accreting mass from the red dwarf and then expelling it. But the ejected relative to the accreted mass, there's only like a small difference between them. So what happens is, even though the red dwarf, say it ejects 10% more than it has accreted, so it will erode 10 times slower. So in the amount of time that the red dwarf lost 0.6 solar masses, the white dwarf only loses 0.06 solar masses. So essentially we can say that the white dwarf remains constant mass, which we can see here for a bunch of models. So the one solar mass white dwarf with the 0.7 solar mass red dwarf would be the yellow curve, both yellow curves. So we can see that the white dwarf decreased a little bit, and the red dwarf went all the way from 0.7 to be down to below 0.1. And the same trend shows for, there's 7 models here, we see the same trend for all the models, the same, basic direction. So we can say, but actually that would mean that any point, whatever white dwarf mass we take will actually, at some point in its evolution, experience all the red dwarf masses from whatever red dwarf mass we take and down. What I mean by that is that comparing the model of the 1 solar mass white dwarf with the 0.7 solar mass red dwarf, with the same white dwarf mass, but beginning the evolution at a lower red dwarf mass, the 0.45. So these are 2 models. I put them side by side so we can just make a comparison. So the first cycles all the way down to the purple, okay, the mass is still higher than 0.45, so we can't compare those. But even if we look, say, from the green one and down, the cycles have the same mass. The green here is 0.35, the maroon one here is 0.3 for both models. And then we can see that the evolution continues identically. So this means that the white dwarf is actually the mass that is determining the evolution. If we try to, I mentioned hibernation already. If we try to compare it to a different white dwarf mass, so if we're looking here at the same red dwarf mass, but the left plot here begins with a less massive white dwarf, the evolution is different. We can see it's the same trend, but if we look at the point where they become essentially detached, so that happens at a different mass. So if the right model here becomes detached at about 0.25 solar masses for the red dwarf, the left one is detached way before. At 0.35, it already starts having epochs of being detached. So this tells us a lot about how much time, how much the evolutionary time the system would need until it starts experiencing epochs of hibernation. So, and also the red dwarf mass that it may start happening at. And what determines this is the white dwarf mass. So the lower what the white dwarf mass is, the more chance there is in seeing such a or not seeing a system in hibernation, because it will reach there for a higher red dwarf mass. Okay, I said that. So what I was actually saying here is that all of these CVs that we are calling different types of CVs may just be, or at least the results of this model support it, that they are all, that a CV is one type of system that is just, we are seeing it at different points in its evolution, just like metamorphosis of a butterfly, which has all these different phases of its life which look nothing like each other. And the reason why we know that they are all the same being is because the time for a butterfly to go through all these cycles is about a month. But when we're looking at hundreds of thousands of years between one nova eruption and the other, we cannot, or have not yet not technically been able to actually observe an entire cycle that goes through all of them, because I didn't mention it, I'll go back a second. Say if we go to an even higher accretion rate, okay, that would be, could be considered a recurrent nova, what we would see is like a little curve over here, okay? So it would be fast enough for us to see a whole cycle, but there's no way that it's gonna go through all these huge changes of accretion rates, and there's no way that it would become detached and be recurrent. So in order for it to go through all of these phases and have this huge range of accretion rates, it needs to be the cycles that go into these, that have these 100,000 years of accretion. And then we would get this sort of picture that after the nova eruption, it will look like a nova-like for a while, and then we'll go through different phases or different types of dwarf nova. If it's not very, very evolved, so it will skip back to nova-like and back to a nova, but if it's more evolved, it will have a very long period of being detached, of hibernation. And then as the accretion rate starts going up, it will become dwarf nova for a while, back to a nova-like, and then we will have another classical nova eruption. Now, as I said, we can't actually observe such an entire cycle like this. A piece of, let's say, a very small piece of evidence from observation that hinting that they may be the same type of system. 100 years ago, there have been evidence of eruption, I think in Korean astronomers somewhere. Today, what we can see is an evidence of an expanding shell, and it exhibits dwarf nova. So what we're seeing actually is a system that exhibits dwarf nova eruptions, but it has an expanding shell, which was a nova 600 years ago. So this is the only sort of piece of observational evidence that supports this. Okay, now I was showing there how the orbital the separation changes over time. I showed that the accretion rate changes over time, and it's related to separation. So the separation is obviously related to the orbital period, and that also changes a lot throughout evolution. What we're seeing here is just
Sorry, we have some problem hearing you. You have a problem with connection, probably.
Oh, really?
Can you check this?
Is it continuing a lot, or was just like one?
A couple of minutes. We have some break in the voice.
Yeah, from the slide before, we heard you weird, and I'm not sure if now it's better. So probably switching off the video.
My internet says that it doesn't say that there's a problem with it. Switch off my video. I can do that. Okay.
Yeah, that probably would help.
Okay. I turned it off. Where's my presentation? 1 second. Do you still not hear me well, or is it okay now?
It's fine. Can you go back to one slide, please? That's where the problem started. Yeah, here. No, that one after.
Here? Here.
The other one.
Yes.
Okay.
This slide?
Thank you.
Oh, okay. So what I was saying is that just like a metamorphosis of a butterfly, which goes through different stages of life, and each one looks totally different. So when throughout 100,000 years of accretion, where the accretion rate starts out high and then goes and then decreases. So it starts out looking after an eruption, after nova eruption, it can look like a nova-like while the accretion rate is still high. And as the accretion rate decreases, it will start having dwarf nova eruption. And if it's enough into its evolution, the accretion rate may go so low that it will be essentially detached until it slowly, the separation decreases more, and it will start showing dwarf nova eruptions again, and close to an nova eruption, there will be no, it will look like nova-like again, and
Sorry,
nova.
we have still
So-
the same problem. Your voice disappears
I don't.
constantly.
Just for, is this the same problem for us, for others? Because I am in the observatory, Luciano from home, we hear the same kind of problem. Do others also have problems with that?
Here,
Matteo, you do also.
I don't know. I actually heard well.
Everything.
You hear well.
Now, yes, without the video on.
Okay, Francesca also says that she has no problem.
Yeah,
Also,
yeah.
then
So it is is a problem with the weather
it's
internal
only the weather in Terma, we have connection.
because it is raining. Okay.
This is true.
No, because
Sorry.
I teach from here a lot, and I don't get complaints. I don't know. I don't think it's my connection. I think my connection is okay.
You know, I mean, it's
Um,
not the connection, it's something with software. But it is strange because me and Luciano are not in the same places. So, by the way, yeah, sure, go on. Let's see.
Okay, I'll try to speak slowly so
No, don't worry.
miss words.
Go on as
Okay.
nothing. Please.
Okay, so as I was saying, when the time between the nova eruptions is extremely long, so this one single system can actually go through all these stages, and that would actually say that that all these different types of CVs that we are seeing is actually this one type of system that is at different stages of evolution. And then I mentioned that we can't really observe an entire accretion cycle of a nova because, as I said, it's 100,000 years or so. Hold on a second. Okay. Just a second. I'm sorry. But there is one very small piece of evidence, which would be Nova SCO 1437, which is exhibiting dwarf nova eruptions. But there is also evidence of an expanding shell, which corresponds with a nova eruption 600 years ago. So this is a very little piece of evidence that helps give credit to this model. And I want to now speak about what happens with the orbital period evolution of such a system, which is directly related to the separation change. So the orbital period changes as well. And this is just also a few models. If I'm not mistaken, the purple one may be the one that I was showing you before. Doesn't really matter which one it is. What we see in general is that the orbital period decreases over the entire evolution, but we can see that this knee over here. So what is this knee over here? Why does it start decreasing very, very fast, the orbital period, and then the decrease slows down? And in this little inset here is the same exact curves, but it's not plotted over time. This is time, evolutionary time, okay? It's about 1 billion years. This is plotted per cycle. So what we can see here is that we just have a lot of cycles in this first point over here where it decreases really, really fast. Why are there so many? Why does the decrease happen so much faster until this point here? So this point is where the magnetic braking is turned off. I mentioned that the model includes magnetic braking and gravitational radiation, which I said they are both weak, but the gravitational radiation is much weaker than the magnetic braking. And as the red dwarf mass decreases, it reaches a point at about 0.3 solar masses where it becomes fully convective. And if it's fully convective, the magnetic braking becomes inefficient. So in the model, it's just turned off there because the mechanism becomes negligible. So at this point, the magnetic braking turns off, which means that during the accretion phase, the removal of angular momentum becomes less efficient because only gravitational radiation is left to do that. So the separation decreases slower. This is what actually, which means the orbital period decreases slower. And this is what's causing the eruption, the time between eruptions to all of a sudden get much longer also. This is what makes it become 100,000 years between nova eruptions. So that's one thing. And we can see how it affects the average accretion rate. So what I have here is just the average accretion rate per cycle. Doesn't show the evolution of the accretion rate, just an average. And we can see that the average accretion rate, if it was about 10 to the minus 9 solar masses per year, or a few times that much before magnetic braking turned off, after that, it drops by 1 to 2 orders of magnitude. So this is what happened. The magnetic braking is at fault here, okay? Turning off the magnetic braking is what causes this. And that happens when the red dwarf becomes fully convective. Okay, and we can see it in the recurrence period also, that if the recurrence period is, say, 10,000 years, it can go up to 100,000 or even longer when the magnetic braking turns off. Just going to look at the time for a second. Does anyone have the time?
You have 15 minutes.
Okay.
Considering also the delay.
Okay. But I think I'm gonna skip over this because I want to talk about this. I'll see if I can go back to it afterwards. So the magnetic braking over there, which causes the recurrence period to become much longer, causes a period gap. So what is this period gap? When in observations of nova, so we can see that below about 3 hours, there are many less observations. So we see much less nova in this regime over here of below 3 hours, which the model shows also. And the cause of this is not that they don't exist there, but the fact that we only see these nova when it's erupting, and since the time between eruptions is so much longer, so say the time between eruptions is 10 times longer, so we will see 10 times less eruptions in this gap. That also explains why there are some observations here. There are rare observations in this. Now this is from the model, it's not observation, but observations show rare cases that are seen there, and it's hard to explain them. Well, this gives some sort of explanation to it. Now, going back to this same plot, there is also, after the orbital period decreases more and more, it sort of gets like stuck. And that's the period minimum. And what causes this period minimum? So what's happening is Roche geometry implies a certain connection between orbital period and the radius and mass of the red dwarf. And what's happening is that for main sequence star, mass radius relation goes more or less, the radius goes like the mass. So alpha is 1. But as the red dwarf is becoming smaller and starting to approach the substellar limit, like starting to transition into a brown dwarf, well, the alpha for a brown dwarf is -1/3. So what's happening is the red dwarf mass is decreasing, and when it becomes small, say 0.15, the radius starts to not contract as efficiently as it did before. So the mass is decreasing, but the radius is like lagging behind. And that's making the orbital period halt at that point, which is why, even though everything below the magnetic braking turnoff we should see very little eruptions here, at about 1.4 hours, which is the period minimum, there are many observations of systems there. And that's because they're all like getting stuck there. It's not that the recurrence period suddenly becomes short, just that many CVs just end up over there. And of course, this is result of a model. This is from Knigge 2011. This is observations where the model is very similar to the observations. It has the period gap between 2 point something to 3 point something hours, and the minimum at about 75 or 6 minutes, which is, so the results of the model are very similar to what is observed. Now, this is also from the model. It's plotted differently. Instead of plotting what I have here is the number of eruptions or percentage of eruptions per orbital period. Here, it's percentage of system lifetime. So instead of counting eruptions, I'm summing the amount of time that the system was at a certain orbital period bin. And this is what I'm calling the real distribution, because although this plot tells us what we see, it's very highly biased because we don't see the same amount of eruption. The eruptions don't occur at the same frequency at each orbital period. And when we do this, we're compensating for that bias, and we're seeing the real distribution. So this is what is actually existing. We just don't see them because they're not erupting. I will also point out that this is from one model, okay? I have these for 4 models, but of course, to get a real picture, you need to get a whole parameter space of models. But it does put into perspective a little the difference between the observational distribution and the real distribution, the population. I can stop here. I can stop here. I'm putting up my summary. I, again, don't have my watch on, so I don't know what time it is. It's okay? We have mass transfer rate. Changes throughout evolution, but on orders of magnitude. It starts high, decreases a lot, even to the point that it can become, for certain points in evolution, for certain combinations of white dwarf and red dwarf mass, it can become effectively zero mass transfer. This can mean that classical nova and dwarf nova and nova-likes and detached systems that are hibernating can very possibly all be the same type of system, just being seen at a different point of evolutions. The model seems to be in agreement with orbital period distribution. And this would mean that most of its life, a CV will be spending undetectably detached. And that's it.